The next speaker is Dr. John Chen from the University of Calgary. He's going to tell us about his research on solvent for heavy oil and bitumen recovery. Dr. John Chen.
Thank you, Andrew. Hello, everybody. This is John from University of Calgary. I'm the ENSOC, Energy Simulation Chair at the university. Again, some of you may attend it. I might have attended my presentation last year at the summit. I present the co-injection of steam and solvent and present workflow that companies may use. And the choice of the solvent for any solvent injection process is critical. And this time, today, I'm going to present a particular solvent, Dimethyl Ether, other solvent for heavy oil and bitumen recovery. And I also added renewable solvent of there. This one is also renewable. You are seeing a moment later. And this is a study where a PDF, a postdoc, and a PhD student carried out. In a moment, I'm going to mention the names. Here's my outline for today's presentation. First, very briefly, touch on what we're doing, my chair program, and then I'm going to present the research objectives for this particular project. And then I'm going to show you a workflow. This workflow may be used by anybody who is interested in collaborate with us. And then we're going to show you some of the simulation results and also conclusions from what we had so far. And also present some of the business opportunities. And again, in a moment, as I mentioned, this study, I think it's very useful when we're looking for the emerging recovery process. So very briefly study, for most of the people in Alberta, they know the challenges of the SAGD. SAGD is the steam assist graphic drainage. It has a high capital and operating cost, and it's typically from 50 to 90 barrels oil. And if the current oil price around 40, and nobody will make a profit out of this. And also, SAGD is the fastest growing source of the greenhouse gas emissions. So these are the two challenges the industry face when they use SAGD. And our current the research objective for our current program is to develop steam additive recovery process that reduce the cost of in situ bitumen production, and at the same time reduce the amount of greenhouses gas released per barrel of production. The additive, as I mentioned, probably some of you here heard me mention many times. The additive could be solvent and chemical, NCG, non-condensable gas, or air or oxygen. And in this particular talk, we do have different groups working on different parts, and some of team working on chemical, some of team working on air, some of team, even the additive could be a catalyst, some of the team working on catalyst and working on different part. And I would like to continue from last year, so focus on the solvent. So this is the general introduction to my chair program, in particular for this particular project. And the mentioned SAGD, even the CSS, the cyclic steam simulation, and they usually use it to recover heavy bitumen. Both SAGD and CSS are associated with high energy density, and we have to inject lots of steam to produce oil. For instance, 3 barrels of water, in terms of cold water and steam, and to produce 1 barrel of oil. That's the best one. And most of the time, you have 5 barrels or 6 barrels, 7, or even 10 barrels of water to produce 1 barrel of oil. So it's higher energy intensity. and also you get a lot of CO2 emission. And the solvent injection, whether steam or pure solvent injection, has been proposed and tested. But so far, we haven't got the promising. A lot of companies did a pilot test, but we didn't see successful stories. The reason is solvent injection is a very slow process. And a solvent injection involves the molecular diffusion. That's much slower than the heat transfer. Heat transfer takes place in the SAGD or CSS. So these are the problem. The other problem is the solvent cost, and the solvent is very expensive. And you want to use very expensive solvent, the light hydrocarbon to produce heavy one. That's normally is very expensive process. The other one is if it is costly, and if we could recover some of the solvent and recycle them, and then the waste of time. So the challenge is how to recover some of the solvent. So, and why we use DME? So, and the DME has recently attracted lots of attentions of the enhanced oil solvent. DME has been used for a variety of products and applications. So for instance, at least some of the application up there. And also DME is getting acceptance of the alternative fuel for diesel in Asia, Europe. And Asia, Europe, DME is used a lot. But unfortunately, DME is it's not allowed to use in US. But okay, at the moment still, we could use in DME in Canada. DME can be produced from fossil fuel or renewable resources, for instance, biomass. That's why I said DME could be renewable. And in general, DME is produced by from two steps, either direct combustion or indirect combustion. So from the fossil fuels or biomass, we produce syngas, and from syngas, we produce DME. So this is how it's manufactured. And what we'll study is, what we're working on to study the phase behavior DME, bitumen-water mixture, and identify the key mechanisms for the rate improvement for the oil recovery, and investigate the advantages of DME and try to compare the DME with other solvents, and also study the DME retention rate and the recovery rate. And this will support the pilot, even in the future, the commercial pilot test. And eventually, we want to develop an economical, viable, clean, sustainable DME related or DME-based recovery process of heavy oil and bitumen. Of course, if it could be used for heavy oil and bitumen, it will be used also for light oil. And this is our workflow. Currently, we are following this workflow to carry out our research. And from the lab experiment, we measure some of the data, the phase behavior experiment, and also the larger scale displacement. And then we will develop some of the either empirical or analytical mixed rule or equation of state to study the phase behavior for DME oil, DME water, and DME oil and water. That are three phases. And then also, once we start the phase behavior, we perform the field scale modeling simulation. And we develop the Rutherford models, study mechanisms, invest the solvent recovery process. And eventually, we want to optimize all the parameters to optimize the production. So this is the workflow we're following. And I'm going to present some of the results we got so far. And so the first, for the phase behavior here, I do have the chemical formula for each of them, for instance, for DME, propane, and butane, and a molecular weight, and a capillary pressure, capillary temperature. So as you see, the property of DME fall between the propane and the butane. And the butane and the propane have been used as a solvent in the solvent injection process. So this means the DME could be a possible candidate for other good solvent. The difference between the DME and the alkane components is this. At the same operating pressure, the saturation temperature of DME is lower than that of the propane and the diluent. So this means DME, where you require less heat, less steam. And also, DME's diffusion coefficient in oil is 10 or 100 times higher than those of propane and butane. So this one, which means we can have a fast diffusion. What's more is DME is also soluble in water. This is the really good property. So this means we have a fast diffusion first, which means this DME produces oil faster. Second, we could use the water to recycle DME. So this is another very good advantage. So you can see from the figure, this is the DME, this is the butane, and this is the water. So this one has a lower saturation temperature. So from here, you see some of the advantages. Of course, there are others. And this is the main of advantages we could use when they design the pilot or even the commercial ones. So we start the phase behavior, and for instance, the solubility in bitumen. And for the DME and bitumen, the phase behavior, we could use the Penn-Robertson or some of other classical ones with the traditional mixing rule. And also, this is the phase behavior for the different temperature, for instance, 100, 125, 150. And this is the viscosity reduction using DME in bitumen, also under the different temperatures. So the dots are the laboratory experiments. As I said, in the workflow, we use the laboratory data. And also we use the phase behavior, the equation of state, to match it up the laboratory data. So they match very well. So you can see from the DME and bitumen. For the water, this is a different story. Because of DME is slightly polar, and that's why the DME is soluble in water. And the traditional Penn-Robertson equation with the traditional rule cannot be accurate model the DME and the mixing rule. And ourselves and our team developed an analytical formula to model or to study the molecular interaction between the DME and the water. And this one provides a study even for the unsymmetric system, which means when you have one phase dominate. So also we have here, we have the lab experiment and also the analytical model. Again, on the different temperature, the match very well. For instance, for the vapor pressure, dew pressure, and on the different temperature, they match very well. So this is the phase behavior. And also, once we understand the phase behavior, as I mentioned from the workflow, we're going to go on to do the Rutherford modeling, do the simulations. And we did a lot of simulations. This is just one of the examples. For instance, this is the Rutherford. We use 2.5, which means we have a half wear pairs. We only simulate half of them because this is symmetric. And the model dimensions, and this is the gray side, is very fine, and it's only 0.2 meters. And this is the inject the constraint, and this is the produce the constraint. We use this, the wear configuration. So this is the injector, this is the producer. Here you inject DME, and here you produce oil and all the other phases or components. The reason why using the SAC-D wear configuration is because SAC-D wear pairs have been used a lot. Probably 80% of the bitumen production come from the SAC-D. And of course, you could use the different ones, for instance, the cyclic simulation or even the flooding, solvent flooding. So we use this one as the one example. And here we use the warm DME. The reason is when you have a cold formation in Alberta, DME is a liquid. And when you have a warm, for instance, 80 degree, and DME is a vapor. And here are some of the simulation results. This is the warm DME results. So again, this is the chamber. And again, remember for those who studied the SAC-D and you have a the temperature chamber. And here the chamber is the DME chamber, the solvent chamber. You see, this is the one of the chamber here, the chamber here. So here, this is the temperature profile. And as I mentioned, one of the advantage for DME is soluble in oil and also soluble in water. So this is the DME mole fraction in oil and DME mole fraction in water. And in general, the DME is more soluble in oil than in water. So the chamber development in the warm injection is similar to that in SECD. And again, this is the way the combination of heat and mass transfer. And the vapor chamber temperature is around in the injection at 80 degrees at the operating pressure, this operation pressure. And as I mentioned a moment ago, DME is soluble in both and water phases. So when we do the simulation, we can find the temperature flyer, and also we can find the mole fractions in the oil phase, in the gas phase, even in the vapor case. So this is the cumulative oil production. And the black one is the DME, and the blue one is SECD. And we comparison with the SECD, with the butane, and with the DME. As I mentioned, the reason why the solvent injection has not achieved a promising or successful story is the solvent injection is a very slow process because the molecular diffusion is much, much slower than the heat transfer. And also mentioned, because the solubility of the DME in both oil and water, so you can see in the first 3 years here, the recovery, the oil production is much higher in 4.3 than the other solvent and even than the SECD process. So this is the really good feature, very good promising. That's promising. So you have fast production, and a company will like this. You have a fast production, you're making profit right away. And the other one is, as I mentioned, it saves time because the lower saturation pressure. So this is the cumulative energy oil ratio. So this one is the SECD, this one is the butane, and this one is the warm DME. So from here, from what we studied here, but in the real situation, and you may have less promising, but still the DME saves you a lot of energy. For this particular example, the energy oil ratio in the DME injection is 75 less than the SECD in that in SECD, and 48 less than that in the butane injection. Again, this is because of the low operating pressure. So this is really huge advantage when we're DME compared to other solvent. And again, when you reduce the energy intensity, you reduce everything, the cost and the emission, the greenhouse or CO2 emission. And also the solvent recovery, that's the major challenge the industry faces. And how could you recover the solvent you injected? Because as I mentioned, solvent is very expensive. And to make profit at the moment, to make a profit at the current oil price is not that easy. But if you could recover some or most of them, and then you can reduce the cost of the solvent. Again, when you inject the butane or when inject the DME, and most of the solvent is in oil. And in the DME case, the DME is soluble in oil, so this most of stay in oil, but we also some of them in water, and some of them is small percent even in the gas phase. So this is we calculated the solvent mole fraction in each of the 3 phases underground, the phases. So again, when you inject solvent, most solvent is retained in the oil phase, At the end of the oil bitumen production, even oil production, you still have some of the solvent or DME remaining underground. and how to recover of them. And remember, during the SAGD or during some of the recovery process, and industry do use NCG to maintain the pressure. So, and in the wear down process, you inject NCG to maintain the pressure to still produce the bitumen, heavy oil, or oil. And if you use the NCG to maintain the pressure, fortunately, this is a really good story. And using this process, probably, again, you will recover most of the DME you inject. This is a really good advantage. And the recovery process, the solvent recovery mechanism is the following. For instance, you depress the solvent vapor and maintain the chamber pressure. That's what I said. And recover the liquid solvent trapped in the reducible liquid saturation. And this is the story. For instance, the vapor pressure, this is the partial pressure, and this is the chamber pressure, and this is the mole fraction. So you maintain this one is fixed. So this one is reduced, and then we reduce this one. So use all the mechanisms, you are able to reduce the mole fraction in the vapor and the mole fraction in the liquid and cases. And again, we did a lot of calculations for the solvent recovery. For instance, this is the DME mole fraction oil at the end of production. And this is the DME fraction after we inject NCG to maintain the pressure. And you're able to, from this simulation, you're able to recover 95% of the DME. And this, you can use them, cycle of them. And this is a really good story. Of course, this is our pure study to see how much DME you could recover. And we have to do a lot of pilot and studies. But the theoretical study gave you some guidelines, gave you indications. Use single whales, single whale pairs, 2 pairs, 3 pairs, give you some guidelines how much you could recover. Again, in real situation, if you could recover 75%, I believe you could make money, 75%. And again, this is a comparison between the recovery between the DME and the butane. For instance, if at the end of the oil production, and this is the butane, and this is the DME, and after you inject NCG, you reject more DME than the butane. Again, this is the solvent recovery process. Again, NCG is one of the examples, and sometimes you may inject water to maintain the pressure. And as I mentioned, DME is a soluble in water. The water will transport all the DME out of underground. So my conclusions is DME is evaluated as a promising solvent for heavy and bitumen production. And a novel workflow is developed to predict phase behavior between the DME and the water. And also we developed the lab workflow. And this workflow will follow you, will guide you from the lab experiment, phase behavior, modeling, optimization, and production optimization. Again, DME injection is able to accelerate bitumen production compared with the other solvent injection, because as I mentioned many times, the solubility in water improves the mass rate between the bitumen and the DME. And a lower energy oil ratio and a less heat loss in the warm injection, DME injection indicate another great advantage of DME. And through properly solvent recovery strategy. So at the end of the day, you say, yeah, I still have lots of solvent underground, and I don't want to buy them. I want to recover them. Probably you could use some of the recovery process, some cheap ones. Water is cheap, just use water, for instance, and you can recover most of the DME. Again, I didn't present the economic analysis, and our group is still working on the economic analysis and try to perform the economic indices from the manufacture of the DME compared with other solvent. And also the injection and retention rates, recovery rates, and oil price, DME price, and try to combine all the indices to see in the real situation how DME could beat other ones. Again, once we finish the economic analysis, we'll tell you another story. As I mentioned, we did this study, and how could we help the companies to do some of the pilot? And large oil sands, we do have, Alberta have a large oil sands, and we do need the emerging recovery process. And this already is focused on the emerging recovery process. Hopefully, if somebody is interested in this DME injection process, we could work together to study more or to carry out some pilot tests. And also the ability to work on the conceptual design. Again, when you have idea on how to make the idea work, and if the idea really work, and how to improve the idea, and what will make the idea work the best, and this is what we're working on. And we integrate the studies with the pilot and the field applications. And so far, we did the fundamental study for the DME injection, and we improved the workflow and also its efficiency. And at the end of the day, and you guys, and if you haven't started this one, if we want to borrow some of our studies, this is going to save you tons of the resources.
Dr. Chen, you need to speed up.
Okay, I'm going to finish. Thanks for reminding. The benefits, again, it's mainly minimum environment impact, and at the same time try to increase oil recovery. And also we do have trained people in this area, so that could help you. And at the end of the day, this I think will help the Canada economy. And I believe if we trust me, I think we're gonna get we have a very promising recovery process. And what you got to take away from here, we're studying a particular solvent, and this particular solvent I think is very promising. And I would like to thank my group, in particular, Dr. Miang is my PDF, and also my PhD student, Mao Jie, and they help. They did this particular project, and also we have a master student help us. Now, of course, this is a large group. This is a large program. I also like to thank other graduates and the current students, all the postdoc researchers, and all my managers and all my collaborators, from industry, and also, and in particular for my ENSOC and energy simulation chair program. Without the energy simulation, and I wouldn't present over here. And thanks ENSOC and CMG Limited, and next and now the CNOOC International. PetroChina Canada used to be, and also of Devon, now the CNR, Sunco, Alberta Innovates, IBM CAS, and everybody. Thank you very much to support our research in past 15 years.
Okay, thank you, Dr. John Chen. We have a little bit of time for a couple of questions. Any swelling tests that may have been published? This question by Andrew Gupta. Do you have the equation of state parameters for DME similar to other hydrocarbon components?
Any sweating test, I don't know, probably we haven't done that yet. So I need to talk to my group. If you could send me an email, I can tell you. I don't know about the sweating test, maybe not, I don't know yet. Okay.
Question about how many, from Takeshwar Kumar from IIT in India, how many % solvent can be recovered on regeneration?
Oh, from the studies, we could at the end of the oil production, we recover 75%. At the end of the solvent recovery percent, for instance, inject NCG, you recover 95% from the study. This again, realistic, not realistic maybe. And if we do the pilot test, we see how much really we're going to recover. And this is a big challenge. But still, as I mentioned, I believe the advantage of DME, solubility in water, in oil, and they're going to give you big advantage of the other solvent in the recovery rate.
Okay, one last question. Appreciate your going to the Q&A later on to address the rest. From Dr. Ershagi, USC, what is the goal in terms of a workable solvent/bitumen ratio?
What's the goal of?
Solvent-bitumen ratio. What do you target?
The target would be, again, would be 2 to 1. That's the best, actually. But
2 to
nobody,
1?
I don't think. Yeah,
2 to 1 or less?
2 to 1. Yeah, 2 to 1 less would be the best. 1, that's the best. But
Yeah.
I think that but I don't think that's workable. And yeah, 2 to 1, 3 to 1 is optimal, but 2 to 1 I think is the best.
Okay. So this closes Dr. Chen's talk. Once again, thank you very much. You're doing some kind of innovative work to help the heavy oil industry.